This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 3 of Week 3. Cylindrical and Spherical Conduction. Radial heat flow through pipe and tank walls, plus one of the most counterintuitive results in heat transfer, the critical insulation radius, where adding more insulation actually increases heat loss. Radial heat flow is everywhere: steam pipes, chilled water lines, pressure vessels, insulated cables. The plane wall formula assumed area was constant face-to-face. That breaks once heat flows radially, because area grows with radius. A cylinder of length L has cross-section 2 pi RL at radius R. A sphere, 4 pi R squared. That growing area changes the formula. Same 3-column shape. The big change from topic 2. Geometry now needs 2 radii and a length, instead of 1 thickness and an area. The solve rows point at the resistance forms and the closed form heat rate. Cylindrical wall, the workhorse. Q dot equals 2 pi Lk times delta T over the natural log of R2 over R1. Rewrite as delta T over R, and the cylindrical resistance is that log over 2 pi KL. 2 warnings. L is the axial cylinder length, not the wall thickness, and convert diameters to radii first. It's plane wall Fourier. The growing area 2 pi RL produces the logarithm. Spherical wall, for completeness. Q dot equals 4 pi K times delta T over 1 over R1 minus 1 over R2. Same shape as the cylindrical formula. Important caveat: this equation is not in Chapter 5 of the Handbook, which mentions spheres only under radiation and external convection. Standard textbook material, not handbook cited. Default to cylindrical unless a problem invokes a sphere and supplies the equation. Critical insulation radius. The surprise: wrap a pipe in still air, and 2 things change as the outer radius grows. 1. Conduction resistance rises with the log term, good for cutting heat loss. 2. Outer convection area grows, so its resistance 1 over H times 2 pi R minus 2L falls. Bad. The total has a minimum at R critical equals K insulation over H infinity. Above it, more insulation reduces heat loss. Below it, insulation increases heat loss until the radius crosses R critical. Plane walls have no critical thickness. The surprise is unique to curved geometry. Where does the warning actually bite? Fiberglass on a steam pipe, K insulation around 400ths, H infinity around 7, gives R critical about 6 millimeters, and almost any real pipe is well above that. It bites only for small geometries in still air, thin instrument cables, fine wires, capillary tubing, where the bare radius sits below R critical. Force the convection and H jumps an order of magnitude, pushing R critical toward a millimeter. Electricians sometimes leave fine wires bare for this reason. A thin jacket below R critical can actually help dissipate heat. Worked problem: a steel steam pipe, 2-inch outside diameter, wrapped with 1 inch of fiberglass, 10 meters long. Outside is still room air at 22 Celsius, with a natural convection film coefficient. The pipe surface under the insulation sits at 150 Celsius. Find the heat loss rate and check via the critical radius whether the insulation helps or hurts. Build the resistance chain, 2 elements in series: insulation conduction and outer convection film. Pipe wall conduction is negligible. Steel conducts roughly 1,000 times better than fiberglass. But flag it. Insulation R is the log of the radius ratio over 2 pi K insulation L. Outer convection R is 1 over H infinity times 2 pi R2L. They sum to about 0.30 Kelvin per watt. 91% of it, the insulation. Compute Q dot. Then run the critical radius check. Total drop is 128 Kelvin. So Q dot is delta T over R total, about 424 watts. R critical is K insulation over H infinity, about 3 1/3 millimeters. The bare pipe radius, 25.5 millimeters, already sits roughly 7.5 times above it. Verdict: we're well into the regime where more insulation helps. Final answer: about 424 watts. Roughly 1,450 BTU per hour. Sanity checks. A bare pipe with only outer convection would lose about 2400 watts. So 1 inch of fiberglass cuts the loss roughly 5.8 times. Pipe is hotter than ambient, so Q dot is positive outward, stepping down the chain. And the outer radius far exceeds R critical, so insulation helps. 5 traps that quietly cost points. 1. Forgetting the 2 pi. The denominator is 2 pi KL, not pi KL, the most common slip on Chapter 5. 2. Mixing diameter and radius. The formula uses radii, so have any given diameter and check inner versus outer. 3. Using L as wall thickness. L is the axial cylinder length, while wall thickness, R2 minus R1, doesn't appear directly. 4. Lumping pipe wall conduction without flagging it. For steel and fiberglass it's negligible, but state it. Stainless on a cold line sometimes isn't. 5. Wrong area. The outer film uses the outer radius where the convection sits, not the pipe radius or an average. Bookmark the page. The cylindrical heat rate formula and the critical insulation radius sit side by side in one section. Fold the corner. The handbook even gives a typical natural convection H infinity right next to R critical, about 6.8, a handy default for a still air problem. The resistance forms are one section over. The spherical formula isn't in the handbook at all. Up next, Topic 4, Transient Conduction. Topics 1 through 3 assume steady state, temperatures fixed, Q dot constant in time. Topic 4 drops that. A hot ingot hits the quench tank. A thermocouple is dunked into a hot stream. An oven preheats. We'll meet the lumped capacitance model, the Biot number that says whether it's valid, and the time constant for how fast the body equilibrates.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.